Okay, here we have a line and a point that's over here, not on that line. And we're asked which point on the line is closest to this point that's not on the line. So as for traveling along here, when are we closer than ever to that point? Well, really, that's just another way of asking how far is it from this point to this line. Because remember, when we measure the distance from the point to the line, we're not measuring just anywhere on the line. We're measuring to a specific point. I mean, if this is you, this is a wall, and I ask you how far you are from the wall, you wouldn't walk over here or walk over here to find out how far you were from the wall. You'd walk straight to the wall. And in this case, straight to the line means perpendicular. So we would want to travel to the line in a path that's perpendicular to the line. And thankfully we know something about perpendicular lines, that their slopes are negative reciprocals. Remember, negative reciprocals mean that they multiply together to make -1. But we commonly think of it as they have been taken and flipped upside down and made negative. So the slope of this line is 2, and we can get that from the equation. And we can think of m equals 2 as 2 over 1, so that when we flip it upside down, it becomes 1 over 2, and then we have to make it negative reciprocal. So the slope of the line that's going to go from here and pass through this line and be perpendicular will be -1 over 2. So we can go down 1 over 2, down 1 over 2, down 1 over 2, so on. I'll connect these with a line. Let's see here. There we go. All right. And right there, that's our point. Now we've seen where the point is on the graph, but we don't know its actual coordinates because we're not lucky, it's not on a box or on a lattice point, right? They're not whole number coordinates. I can't just read them off. So we have a little bit of a problem here. We want to find out where those are. We're going to do a little bit more work. Well, here, we know the equation for this line, and we can easily get the equation for this line, thankfully, because we do know the y-intercept. The equation for this line is y equals its slope, -1/2 x, and then plus 1, 2, 3, 4, plus the y-intercept, 4. So we think about all these points on this line I can get by putting in an x value and then doing a little math and outputting a y value. And the same thing over here. I can put some x in here and I can do the math and I can output a y value. So there must be at some point an x value that I would plug in. It's actually right here. I'm going to plug that into both of these, and I'm going to output the same y value, which is right there. We just need to find out what those are. Well, the way to find them out is we write that -1/2 x plus 4 equals 2x plus 2. So the two things are equal to each other. They give the same output. And so we just have to solve and figure out what x is. So let's see. I'll add 1/2 x to each side. So that's 2 and 1/2 x. Man, I don't like mixed numbers there. We'll just say 2.5 x. See, plus 2. And then I will subtract 2 from each side, and I get 2 equals 2.5 x. And then we'll just divide 2 by 2.5. Get my calculator out here. So 2 divided by 2.5 is 0.8. So 0.8 equals x. So we know that here x equals 0.8 is the x value that gives us that point. The x value that I plug into these to get the same y value for each one. And so let's just test out, see what happens. Y equals -1/2 x plus 4. Y equals -1/2 0.8 plus 4. let's see, negative 1/2 times 0.8 would be negative 0.4 plus 4, and this is going to be 3.6. So then next door, let's try it with the other equation. Y equals 2x plus 2. Y equals 2 times 0.8 plus 2. Y equals, let's see, this would be 1.6 plus 2. 1.6 plus 2 is 3.6. So indeed, 0.8 plugged into both equations gives us the same output. And so this over here is y equals 3.6. And so the point where these two lines intersect is 0.8, 3.6. Okay? And that's the point that is closest to our original. What was our original point here? It was 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. It was negative 4, 6. And that is the point that's closest, that's on this line and closest to negative 4, 6. So just a recap of what we've done. We were trying to find the point here on this line that's closest to negative 4, 6. And we know that that will be the point that that point is the point we would measure to if we were measuring the distance from 0.46 to that line. And that distance needs to be perpendicular. So we had to write the equation of a perpendicular line that passes through the point negative 4, 6. And to get the slope for that perpendicular line, we had to take the negative reciprocal of the original. And then to get the y-intercept, well, we were lucky and it was right there on the graph. So we wrote the equation for that perpendicular line and got negative 1/2 x plus 4. Now to find where the two lines intersect, we just set them equal to each other, set these two equations equal to each other and solve for x. And that gave us the x coordinate for the point. And then we just plugged in that x coordinate into both formulas for the lines, and we output 3.6 for each of them. So 3.6 is our y coordinate. Now, of course, we wouldn't have to plug in that for both of those because one of them should be enough, but it's a good idea to do both because if you've made a mistake and you plug it into both and you get different numbers, different outputs, different y values, then you'll know something's gone wrong at some point and you'll need to review your work. And here, although it's possible, I suppose, that we made a mistake, but it seems less likely since we got the same y output each time. All right? And that is how to find the point on a line that is closest to some random point out in space.